we are back for another really wonderful session today with hardware and software combined. First, we will have Masako Yamada for an introduction to IonQ, who is a great contributor and sponsor of this summer's program. And then we will have the hardware panel with people from IBM, Atlantic Quantum, and Atom Computing to discuss what are the best qubit modalities, what are the challenges, what are the developments and advancements. After that, after a little break, we will go to the QML, the Quantum Machine Learning workshop in Penny Lane with Catalina Albornoz from Xanadu. Really excited, and it is a pleasure to have you here, Masako. You wrote in a message to us, and let me pull that up. You wrote that you joined IonQ after a 20-year career at GE Research, and this was beautiful. You said, "It is never too late to learn something new." You change domains about every 5 years, from materials modeling to experimental optics to additive manufacturing to industrial AI to quantum computing, and continuous learning will lead you to a future you could never have imagined. So great message to everyone. And now we are excited to hear your spotlight on IonQ. Please take it away.
Thank you so much. And thank you for the invitation. So I am so happy to represent IonQ today in this forum. And I just wanted to introduce myself. I am the Director of Applications. And what applications means in this context is to develop really meaningful, impactful, algorithms and software that help address our clients' needs, right? Clients' business needs. So that's what we mean by applications here. And I am leading the group that develops applications for our clients. So actually, I was reading the charter of this conference, and I found it very interesting that it said women, STEM, and entrepreneurship. So I wanted to touch a little bit on those topics and really why I'm here today speaking on behalf of IonQ. So if I were to talk about my career trajectory, I went to Wellesley College as an undergrad. And for the folks who do not know, it is an all-female college. So right there, I think, you might get a sense that, gee, this is something that I care about, right? And I do. I care deeply about just increasing representation of women in STEM. And that started a very long time ago. I received a PhD in physics at Boston University in computational science. So at the time, computational science that I was a part of was HPC, using conventional CPUs only, so CPU only. Since then, I moved on to GE Research, where, as the introduction had indicated, I changed topics about every 5 years, but the goal was the same. And the goal was, how do you take R&D and put it into product, right? How do you take something that's super innovative and put it into product? At GE Research, it's several thousand people and 80% PhDs. And those PhDs were really dedicated to, as mentioned, taking just really amazing engineering and putting it into the next thing. But after 20 years there, the question becomes, by the way, this is on the lower right, this is the first team that I led as a people leader. So on the left-hand side, that was the original manager. He decided to step into a different role, at which point I became the leader of this team. And as you can see, the female representation is pretty low, like really low. And this has been a theme throughout my career and something that I've been working very hard to mitigate and to improve upon. But this was the first team that I led, and I did learn a lot in that process. So going to now, about 1 year ago, I moved over to IonQ, which is a quantum computing company. And then the question becomes how do you spend a career, right, at one company and suddenly start working for basically what's essentially a startup, right? Very entrepreneurial. And why? So the how, just briefly, is that I actually had a recruiter call me. So I probably had a LinkedIn someplace or something someplace that a recruiter found, and I just got a cold call. And I took that call, and here I am right now. So the how is really, wow, you can have a very long career at a very established company and still get the recruiter call, searching for something and end up here. So, and why? So why did I, at this point in my career, decide to make a leap from a very large established company that I had a really solid career in to, you know, a very small company, a fraction of the size, 1,000 of the size, rapidly growing, more uncertainty. And the reason is because I'm going to touch upon it in the next slide, which is if I were to look at my career trajectory in computing until a couple years ago, as I mentioned, I was in the classical high performance computing domain. And starting when I was an undergrad to the lower left, I was literally modeling like two particles, right? Two particles interacting with each other. In grad school, it became hundreds. And as a professional, like I was able to start to model millions of particles in molecular dynamics. And this kind of mirrored the change in the hardware. So if you look at the right-hand side, initially desktop, then you have HPC, and then you start having HPC where you have CPUs and GPUs. So I really was enamored at the fact that even within 20 years, I was able to model like 1 billion times larger simulations that I had been able to do in the past because of changes in the hardware, right? It was driven by the changes in the hardware. And then I thought to myself, wow, quantum computing is really poised to have a really disruptive change in what we can do in terms of, computing. And I wanted to be part of that change, right? I wanted to be part of the hardware change that enables people to do amazing new things with software. So this is really one of the reasons why I made the shift to a new company in quantum computing, but also the entrepreneurial nature of the company, going from a 300,000 person company to a 150 person company was just really exciting to me because I felt that I could make a difference as one of, I wasn't one of the co-founders, but my direct manager is, and to be a part of that entrepreneurial, rapidly growing, field, I think it aligns with this conference's charter, and it really wanted, it was something that I wanted to be a part of. So talking about IonQ's computers, quantum computers, I'm just going to briefly touch upon what our quantum computer is, right? And basically what it is IonQ. So we take a bunch of ions and we line them up in a row. And then the way we compute is by interacting different ions with each other and sending commands. So for example, and I'll show an example code later, I have the ions in a row and I can say, okay, I'm going to send a laser pulse to one of the ions to change its state. And then I can send 2 laser pulses, one to ion number 3 and the other to ion number 17, and say that they interact with each other. And I build code by basically sending different laser pulses to the different ions, changing the states, and at times interacting the pulses with each other. And that's literally how I write my code, by defining these laser pulses and how they interact with these different ions. So each ion is a qubit in this case, right? And then I can turn it up or down, or actually not just up or down. The difference between, conventional computing and quantum computing is that each of these ions, not only can I do like 0 or 1, I could do anywhere between 0 or 1, and I can also change the angles. So you're really probing a sphere of possibility when you're talking about the states of the qubits. So next, very briefly, some of the differences or some of the differentiators of IonQ's modality. So as I mentioned, each qubit is an ion, and the definition of an atom is that you can't divide it any further, right? So that is it. There's no manufacturing defects. There's no semiconductor processes. Each ion is the qubit. Also, as I mentioned, we shine laser pulses at the qubits and then to change their state and also to interact them with each other. So every single qubit can interact with every single other qubit. This is actually quite unique because in many other modalities, the qubits are connected physically. So you can only interact with your neighbors or maybe some of your neighbors and nearest neighbors. With us, we can interact any qubit with any other qubit. We also have several other benefits. I'm not going to touch upon them all because I do want to get to the application side of things, but I wanted to just, show that we have a longer term roadmap on how we want to increase the number of qubits. And we also have very good gate fidelity because we are controlling each individual qubit, which is an ion. What are some of the applications that we're working on? Because I think, why do we even have computers? It's because we're solving problems. So some of the applications that we have solved for real customers include chemistry batteries, object detection. This is machine learning. We've done image processing and image generation. So for example, in this image processing work that we did with Zapata, we created a machine learning model to learn the MNIST handwritten characters. And then we used quantum computers to generate synthetic handwritten characters, right? So these are just some example applications that we've worked on with private customers that we're also seeking to apply toward government initiatives. So this is like the from to is how can we take something that we've developed for private customers and apply it to government interests as well. We've also done risk management. We've looked at correlations across time series. We've even done optimization of luggage into bins. How can we take 8 pieces of luggage and put it into 4 bins with constraints? And what I really wanted to touch upon here is that we are serving the needs of real customers, solving realistic problems using quantum computers. And we believe there's huge amounts of potential to apply them to a range of government initiatives as well. Very briefly touching upon, how do I program this kind of quantum computer? So we don't have PyTorch for quantum computing now, right? We don't have, Python or Julia or what have you at the moment. Currently, what we're doing is really, to the point that I was making earlier, we are sending pulses, laser pulses to ions, right? So if you were to look at a quantum circuit, this is kind of what it looks like. And this is a machine or 2 circuits, right? One in convolutional neural nets and 2 is circuit board machines. But this is literally what we're doing in terms of programming our computers. Currently, it requires, as you can imagine, a lot of expertise and deep knowledge of circuits. But eventually, and my goal is to create applications that wrap all this stuff around so that consumers can benefit from these, calculations without having to think or worry about sending the laser pulses themselves. So that is my goal, which is to make these applications accessible, impactful, and meaningful to a larger range of customers. So finally, I just wanted to touch upon some of the more recent applications that we're developing. We are doing a lot of work in quantum optimization with our partners. We're working on graph neural networks, including natural language processing, sentiment analysis. We're really trying to understand what the benefits of quantum machine learning are relative to conventional machine learning. One of the things that we're finding is that the number of parameters you need to use to represent a model is a lot fewer using quantum machine learning. And we're very optimistic that this means that we can get greater insights with less data. As I mentioned, we're also looking at correlations across data sets to say, oh, if I have 3 time series, or if I have 1 time series, 1 video, and a set of operational data, can I really capture something deeply embedded from within that set of data? And finally, one thing that we've started to really recently look into is linear solvers, since these are so important to so many different kinds of physics-based simulations. So I think I just wanted to stop with an invitation for anybody on this call to try IonQ's simulators for free. So you do not gain access to an actual IonQ hardware system, but you can gain access to our free simulator, which can help you. You can learn how to program these circuits, right, and optimize them. So just go to ionq.com/resources, click on Get Started, then click on Cloud Access, sign up for free, and you will get started with getting an API key and running these jobs on your own. So I wanted to close right now. I recognize my slot was 15 minutes, but thank you for letting me to introduce myself. I would love, my purpose of my introduction is to let people know you do not need a PhD in quantum physics, quantum applications, to be in this role, making an impact and doing something really amazing. So thank you so much.
Amazing. Thank you so much, Masako, for this great overview and for the great overview of your own career as well, which is really inspiring for everyone. IonQ will be back with a virtual lab tour and at a career fair, with which we are really happy. For that reason, I will just ask one question that is being asked now on Discord. And Erica from the US asks, is the reduction of optimization parameters done in classical pre-processing because the quantum computer doesn't need them? Or does the quantum computer and associated code indicate that fewer parameters are necessary?
Yeah, so just to let folks know, quantum machine learning is a hybrid modality. So what we actually use is both quantum and classical computers to do the end-to-end. So we've actually tried both. What do I mean by that? We've done all quantum. We've done training on quantum and doing the classification classically. And we've just tried to move the levers, saying, okay, what is the degree of quantumness we want to include in the calculations? And we can make it, like, as I mentioned, all quantum, or we can make it 90% classic and 10% quantum. But for the reduction of parameters, that is a quantum done quantumly. And it's just something that we're continuing to evaluate.
Amazing. Thank you so much for this inspiring talk, which is echoed by everyone on the Discord where the questions are asked and the comments are given. Many people are already on the Get Started page. So we look forward to continuing the IonQ participation in WOMANIUM Quantum with the virtual lab tour next week and the career fair. Thank you so much, Masako.
Thank you so much, everybody.
At IonQ, we build quantum computers that are based on individual atoms. This is one of our earliest prototypes of a quantum computer, and if you come close, you can see at this core there's a vacuum chamber. It looks like a lot of plumbing. That's the key to a quantum computer, is the isolation of the individual atoms. They can't have air striking them all the time. These atoms are floating in space. They're not part of a surface. They're not part of a solid. And if you look closely, there's a chip hanging upside down. It has a bunch of electrodes, and the atoms hang on those electrodes. It's sort of like a magnetically levitated train, only our train, those are individual atoms, and these are electrically levitated, not magnetically. We control our atoms that form the basis of the quantum computer with laser beams and optics. Those beams and those optical elements are themselves controlled by very fancy electronic devices. We have to build all that stuff in-house. We have to own the entirety of the controller system. You can't just buy an entire system that way. We can buy components, but we have to build it ourselves. In one of our more mature electronic controllers in here, you can see a bunch of cables coming off of devices. Each one of those cables will send a signal that will eventually guide a laser beam to a single atom, one cable per atom. These are, again, the way we control the algorithm that we're programming, the initialization of the quantum bits, the qubits, and also their measurement. We don't mind that the electronic racks are maybe large. We know how to shrink those in the future. They'll all be integrated onto a single chip. We don't need to do that just yet, but in the future we have definite plans on miniaturizing the whole footprint of the entire system. To package our quantum computers, we require a dust-free environment. The chip and so forth are inside of a vacuum chamber. And so we have this clean room here that allows us to assemble things in a very clean manner so that the system will behave. We don't do fabrication of our chip. We can farm that out, but we have to integrate it and we have to package it. And in here you can see a couple of gold chips. These have a bunch of electrodes that will eventually support individual atoms. We apply electrical potentials to these electrodes, and then when the atoms are there, they are trapped. They can't go anywhere. And here we have a couple of our latest generation quantum computers that have many more qubits than the previous versions. As you can see, these big black enclosures allow us to control the environment under which these computers are operating. This system and this big box is running jobs as we speak. These jobs are uploaded to a cloud provider that allows anybody with an account with AWS, Amazon, or Microsoft Azure or Google Cloud Platform to run jobs on this particular hardware. Our quantum computers are getting very small with every generation, and in the future we have very well-defined plans to put everything you see in this big black box on a single rack-mounted device that can be wired to other rack-mounted devices with optical fibers, very much like a data center. We're going to have the atoms talk to other atoms on a different chip via optical fibers. We've done all of the research behind that type of an interface, and at IonQ we're translating that laboratory work into a reality, into a commercial product. One aspect of computer design, quantum computer or any computer design, is that the software level is incredibly important, and it has to be integrated so that the users can get on and use these things to solve problems and not worry about individual atoms. So our job is to make our systems so stable and accurate that the users will be able to solve certain types of problems much faster than they could using any other type of computer. At IonQ we have a very diverse set of skills, from atomic physicists like me all the way to software and algorithm engineers. And so it's very important for us to have an environment where we bump into each other and we have these collisions between people with very, very different skill sets. And I think our goal here is to allow the user of quantum computers to not know or care what's inside the computer, very much like how we use cell phones today.